My name is Stephen Morris. I am from the University of Toronto, and I'm going to talk to you about icicles, the growth and morphology of icicles, which has been an obsession of mine for some years. And in English, we call it an icicle, which is a kind of diminutive of ice, a small thing of ice. And this is what it is. It's a thing that hangs off the side of your roof. It's pointy. Water runs down it, and it freezes, and it makes this pointy shape. In French, I believe, it is called a stalactite de glace. Am I right?
Yes.
And this gives away something right away, which is that they are similar in many ways to stalactites, which are the things that hang in caves, right? You may be surprised to hear that in the province of Quebec in Canada, they do not call it a stalactite de glace. It is called un glaçon, a little piece of ice. The same word used for the drink, the thing you put in your drink, okay? But since you're never drinking things with ice in them in the winter, there's no confusion, right? And I think also in Switzerland they call it a glaçon, am I right? Now, since we are in Corsica, we should learn the local word, and I won't try to pronounce it. Can anyone pronounce it? Chekulu. It also means a little piece of ice. And you will find as I continue that Japanese is a very important language for the study of icicles. And in Japanese, an icicle is a surara. See? Surara. Surara. Okay. All right, so why study icicles? I'm often asked this question. And for me, the answer is I'm just interested in them for blue sky reasons. I see them, I pick things from nature, and I'm just interested in them for no application reasons. But they are also part of a general program that I worked on for many years, which is nonlinear pattern formation applied to geomorphology topics. And because stalactites are very difficult to grow in the laboratory, it's much nicer to grow icicles because they're very amenable to laboratory work. And here's some roof with icicles. Everybody has seen them, at least in Canada, they have seen them, but nobody thinks about them carefully. And that makes it an interesting subject because another thing I use the icicle research for is what we call outreach, when we talk to the public. We talk to art people, we talk to music people, and we have a topic that we both have seen and that we have something in common together. So I spend a lot of time talking to the public about science, and in particular icicles are a nice topic for that. I should also mention that there are many, many people who study ice buildup on structures for the purposes of engineering. About some years ago in Canada, there was a huge ice storm in Quebec which knocked down $1 billion worth of power lines. And this is simply from the weight of the ice that builds up on these things. And another big area, if you look in the literature, is high voltage structures which have ice buildup on them. And these are little lightning rods, if you think about it. So this is a very dangerous kind of thing. So most of the literature in English about icicles is actually power line engineering. And their job is to get rid of them. But I'm interested in their shapes and so on. Engineers usually don't care about the shape, they just want to know about the weight. Okay, and I was moved to think about icicles by these papers, which are very provocative for me. Many years ago, Ogawa and Furukawa wrote down a theory for the rippling pattern that appears on icicles. I'm going to spend a lot of time talking about this. Icicles are basically cone-shaped, but some icicles have a ripple pattern on them. And this is a kind of pattern formation, so this is why I was interested in it. And there were two papers. Well, there was first Ogawa and Furukawa's paper, and in response to that, Kazuto Noeno wrote a long series of papers trying to explain this rippling pattern. And so my second talk will be mostly about ripples, and so these two papers and this series of papers put me on that course. Another problem in icicles is the idea of their universal shape, of so-called Platonic icicles, as if Plato in the world of the forms, had a perfect icicle. And there's a very provocative paper by Short and Bajens and Grae Worster where they purport to calculate the universal shape of icicles, and I will talk about that today. So those are the papers that put me onto it. I'm a professor, so I don't do any real work. Only the work is only done by you, the students. And my two students who worked on this for a very long time, Anthony Suhan Chen, who's now at the Southern Alberta Institute of Technology, he managed to grow 230 laboratory icicles, and this is the title of his thesis. And then later, John Layden, my previous student, he now works for a software company, and he managed to grow about 180 icicles. The experiments were also done by a long series of undergraduates and undergraduate engineers who helped to design and build the machine and all that. So this is the work of many, many people over many, many years. I will give 3 lectures. The first one today about shape mostly. I'll talk a little bit about stalactites and platonic icicles. Tomorrow, I think it's tomorrow, I talk about ripples and what causes them and what doesn't cause them, and what the theories say, which I have to tell you is an unhappy story because the theories don't work very well. And then on the 3rd lecture will be about what happens when you try to understand the flow and the interior of icicles. Here's some icicles on a roof. So here, we should talk about where ice comes from. Icicles grow when ice forms from water, and water at 0 degrees turns into ice by releasing a certain amount of heat called latent heat. I hope this is not a surprise to you, okay? All right, so icicle formation is basically a heat transfer problem. You must somehow get rid of the latent heat from the water into the surrounding air, which is very cold, and then the ice will form. So it's a bit of a chicken and egg problem. Where does the water go? It flows over a surface of ice and loses heat, and that ice surface is itself made from the water that it comes from it. So which comes first, the chicken or the egg, right? There is a similar situation in stalactites. In stalactites, calcium carbonate is dissolved in the water by the presence of carbon dioxide mixed in the water, makes it acidic. And as the water runs down the outside of the stalactite, a little bit of the carbon dioxide comes out into the cave, and that changes the chemistry, and that precipitates calcium carbonate onto the surface. So where you have heat escaping here to make ice, here you have carbon dioxide escaping to make calcium carbonate, and that adds to the shape. Icicles actually have 3 distinct ways that they grow ice. The first one is the obvious one, maybe. The tip grows fast, and water runs down the icicle and escapes and drops off the tip. And there is actually a little droplet on the bottom of a growing icicle. If you see an icicle and it does not have a liquid water drop on the end, it's probably not growing. It's just frozen, okay? During growth, there is a little droplet of water hanging from the end here, and ice forms inside that drop. Interestingly, it only forms near where the edge of the drop, and that leaves actually a column of water inside the icicle. So the bottom of the icicle is often a kind of tube filled with 0 degree water, and that water is in equilibrium, or very close to equilibrium with the surrounding ice, so it does not freeze. It does eventually freeze. So that's mode 1, and mode 1 is fast, so the icicle tip grows, okay? Mode 2 is some of the water that is running down the outside of the icicle also freezes and makes the icicle thicker. Okay, that's mode 2. It is mode 2 which sometimes, under certain conditions, gives rise to the rippling pattern. And then there's a subtle mode, which I won't talk about much anymore, called mode 3, where this column of water eventually loses its latent heat and freezes solid inside the ice. So an icicle is mostly solid. There might be a little tube of water at the bottom. Mode 3 fills up the pipe filling. Okay, this is all, nomenclature comes from Mayano's paper. So stalactites have a mode where only the tip grows, and there is no mode 2 and no mode 3, only mode 1. So the water runs down inside of a narrow pipe made of calcium carbonate and drips off the end, and the end it lengthens by mode 1, okay? And that's called a soda straw. And Mongreux will talk about that, about soda straw stalactites later today. But ice does not form these things. Why? Because the latent heat would escape through the sides of the straw and freeze the inside solid. But in a stalactite, the water is not consumed. Only the tiny dissolved component is involved, okay? So because heat, and it behaves differently than carbon dioxide, the carbon dioxide cannot escape the inside of the soda straw. It can grow longer and longer and longer, whereas in ice, the water is consumed to make the ice, and the latent heat can move through the ice and escape. Okay, so they are different than each other. They resemble each other sometimes, but not always. The details are different, okay? There are some formations of cave formations which look like drapery. They're not loose, they're solid rock. But this happens when the water drip runs down the leading edge of this thing and adds to it only the leading edge, and that's called a drapery. And you see these very commonly in cave. They also happen in icicles sometimes. Okay, now I'm going to show you an experiment where I build a machine which is partly explicitly designed to avoid this. Okay, we're trying to make the most axisymmetric cone-shaped icicles we can. We don't want to see drapery, but that does happen. Okay, so in more detail, how this works is water flows down the sides of the icicle, releasing latent heat, and the latent heat has to get out into the surrounding air, and first it encounters the flowing water. So it is carried down the icicle somewhat by the flowing water. And then it goes out into the surrounding air, and it joins a warm boundary layer of air flowing upward. The icicle is the warmest place in the environment. It sounds kind of funny, but it's around 0 degrees, and the surrounding air might be -10 or -15 or -20. Okay, so there's advection and diffusion. It both is conducted and diffused, and it's advected first by the water and then by the air. It may surprise you to hear that the water also, so that cools the water and freezes it sometimes, but the water also cools by radiation. It turns out if you calculate the radiation budget, it's significant. Radiation carries away the latent heat a significant amount. Now at the tip, something more happens. It's more efficient at the tip. The heat transfer is more efficient at the tip because the boundary layer is very thin there. That's the beginning of the boundary layer. And because there are more directions for the radiation, and because some of the heat is carried away by the drops that fall off the end. And so if you think about the heat transfer, it turns out the heat transfer is less efficient at the sides and much more efficient at the tip. So the tip grows 10 to 100 times faster than the sides. So why is the icicle long and pointy? It's because the tip grows faster than the sides do. It's very simple. Heat transfer is better at the tip, and therefore the icicle becomes elongated. And of course, gravity carries it down. Okay, so I have to now admit that most icicles that we see in the environment are not from natural causes. They are from waste heat. So here's an old church in Montreal where they don't have very good insulation, and the snow melts and it drips off the edge of the roof and forms icicles. If you see icicles on a building, it means that there's bad insulation on the building, okay? You do sometimes see icicles next to waterfalls or from seeping cliff faces or somewhere, but in the natural environment, there usually isn't liquid water around in a freezing environment to make icicles. Almost all the icicles are caused by sort of man-made waste heat. The first icicle machine I built while I was on sabbatical in Cambridge in, I have to tell you, 2006, okay? So that means I've been working on icicles for 20 years. It's hard to believe, but it's true. So the first icicle machine was the simplest possible thing. All I did was make a nozzle which was guaranteed not to freeze by heat exchanging to a circulating bath which was kept at a few degrees above 0, and the water tank just dripped water through this thing. And we were in this cold room which had just been built at Cambridge at the time, and then the cold room has swirling, freezing air, and you get an icicle. And I was able to grow a few kind of small icicles that way. So fast forward 20 years, I will now show you what the icicle machine evolved into. It's a kind of a monster, I have to say. So this is the schematic. It's a box about the size of a small refrigerator. It is cooled by circulating antifreeze on the outside of the box. The inside of the box is full of air. We can circulate the air inside the box or not, if we choose not to. We have a water reservoir. We pump water slowly through a nozzle here, which is warmed, controlled temperature by the computer. It drips off onto a support, and the water drips off the support onto a funnel, which carries the unfrozen water out of the experiment. The funnel is also slightly warmed. The support rotates very slowly, okay? In fact, this looks like it's going really fast, but this is 4 or even 6 hours of time in real time. If you watch the icicle grow with your eye, it's very boring. You can't see it move. The rotor takes 8 minutes for a rotation, and the drips fall off every few seconds, okay? So the icicle is a very boring experiment, okay? But it's not boring because the computer's going to do the experiment. We don't have to watch all the details. So I'm going to tell you why we rotate in a moment. This is what happens when you use distilled water. You get a very smooth-looking, reasonably smooth-looking, pointy shape. If you do the same experiment with tap water, and even in Toronto, the tap water is thermodynamically almost indistinguishable from distilled water. It's not very dirty, okay? It's got a tiny bit of impurity in it. You will notice that the icicle grows ripples as well as the tip extending. So these are the ripples that I showed you a picture of a minute ago. So this is the experiment. We build the experiment, we try tap water, and we see the ripples, we think, great, it's working. So then we try distilled water, and whoa, the ripples disappear. Surprise, okay? This was the first time people noticed that ripples had to involve impurities. It turns out that pure water is totally different than even tap water. Now you'll notice that this icicle does not appear to be rotating. It is in fact rotating, but we have an indexer, which I'll show you in a second, which triggers the computer to take a picture at a given rotational position. And in Anthony Chen's work, there were 8 rotational positions, and in John Leyden's work, there were 16. Okay, and so what I do is I assemble a movie of only the pictures taken from a particular rotational position, and then the next one, and then the next one. So it's like a stroboscopic movie. So this icicle is rotating, but we're only seeing one side of it each time. It's the same icicle growing 8 times, okay? And that's what happens with tap water. Okay, so this is what it really looks like, or the final version really looks like. It's a big box full of insulation. The cooler is somewhere over there. The orange stuff is antifreeze. These are the fans. They blow air through a heat sink on the side. We don't have to blow air, but we can either turn it on or off. And the camera peeks through the side of this thing down a tunnel. The camera is a 36 megapixel Nikon D810, in case you're interested. And so that's where the data comes from. All the temperatures are controlled, all the motors and everything are controlled by a computer. And so if things are going well, you come in, you load up all the water, you start the cooler, and a few hours later you can turn on the machine and it begins to run. And 4 to 6 hours later, you have an icicle and it's all stored for you. It's all run by the computer. Yeah? The window, let me see if I can go back here. This window is 65 centimeters tall. So the icicle is about 2 feet in length. Okay, so I mentioned the rotor. So this is the top of the machine looking down. The support is down here, and there's a big bearing, a big lazy Susan bearing, as it's called, which rotates very slowly by a motor. And as it rotates, these little things we call tabs move through a little device which detects whether the tab is there. And the computer reads this device, and when it detects that a tab is passed, it fires the camera. Okay? That's the indexer. So why rotate? Well, the 8-minute rotation is fast compared to the time it grows, okay? But it's slow compared to the time the water takes to run down the icicle or the air takes to move. And that's about 10 seconds. And centrifugal effects, you might think it's going to spin, are negligible because this quantity is very small. The purpose of it is to encourage axis symmetry by averaging out the temperature gradients around the circle. Okay? So it's for the same reason as you rotate your meat in your barbecue. You want it nicely done on all sides. Okay? A slightly less obvious reason is that the nozzle, that's up here, is actually not on the axis, but off axis. So that means the water is distributed in a kind of fair way around the top of the icicle. If you don't do that, you tend to get drapery, okay? We don't want drapery. So we use an off-axis nozzle to distribute the water fairly at the top. And finally, the most important reason is, as it rotates, we take up to 16 pictures. The computer can detect the edge. Computers are stupid, okay? All they can tell is the difference between black and an icicle. We can detect the edge, and if we rotate, we get 16 views, 32 edges, okay? And from that, we can reconstruct the full 3-dimensional shape of the icicle. If you don't rotate, you have to use mirrors or some trick in order to see all sides of the icicle. Okay, by rotating, we see all sides.
So in real life, it does not rotate. So you should expect to have drapery as a general feature, which is not the case. So
You should have what?
Drapery instead of icicle.
The drapery is somehow an initial condition situation. If the thing you're dripping onto is dry and it doesn't coat well with water, then you tend to get drapery. If you use something like a piece of cloth or something which is fully wet, then you don't get drapery. It's not nice. We don't want that. Okay. If the support here is made of wood, if you don't rotate, sometimes you get drapery and sometimes you don't. Okay. So this is the rule of icicles are like snowflakes. Every icicle is different to some extent. Okay. All right, so here are the 16 rotational views of this icicle growing. Let me go back. Sorry. So this is a movie assembled from 16 different rotational views. And you can see it's rippled, and I can see every side of it. So that means we can do edge detection. And when we do edge detection in the computer, we extract the edges. And we know the rotational position of every edge. And so we can actually build a three-dimensional image of the icicle and send it to a printer. And here is an actual size icicle, which melted years ago, now made in plastic, okay? Now, you don't have to make a three-dimensional image. And in fact, there's a lot of interpolation in a three-dimensional image. And what we really study are data like this, where we have left and right edges that are detected by the computer, okay? And almost all the data I will show you is either temperature measurements or something, or taken from the topography of measurements like this. And a lot of averaging, because we have enough data averaged all around. So we often rotationally average the data. Icicles are very stochastic, so you need a lot of averaging. Anyway, here's a 3D printable icicle. You can make what's called a point cloud, and you can send it to a piece of software which meshes it. And so this is a meshed icicle. And the cool thing is you can actually turn it around on the computer, look at all sides of it. You can do things that you can't do in real life, like zoom in. Okay, so this gives you an idea. We know the shape exactly up to some resolution, up to a pixel resolution in 32 megapixels, okay? All directions and as a function of time. Okay, so what do we do with this data? We have a great deal of data about the shape. The temperature range is from about minus 18 to minus 8. It's hard to grow an icicle if the temperature is too high, or if the flow rate that you put in is too large, because the water carries away the heat, and if you don't carry away heat too fast, then no icicle will form. We use an input flux, which is sort of a practical range. This is fast and this is slow. You could go slower if you wanted to. An important parameter will turn out to be, perhaps the most important parameter will turn out to be the water purity. And we did everything from rather pure distilled water up to rather impure water, but nothing like seawater. Seawater is 1,000 times this level of impurity. And this is our bog standard distilled water. Later, I will show you some experiments by Menno, who is here somewhere. Where is he? There he is. He also did super pure water, so-called milli-Q water, and that turns out to be interesting. We also use various impurities. So instead of just using tap water, we use scientific tap water, okay? We get distilled water and we add the impurities, or we dope the water with the impurities that we want. And we use 7 different kinds of impurities, including fluorescent dye. There are some other parameters like the air motion I'll talk about briefly. Nozzle temperature, we keep the nozzle temperature very close to freezing, but not freezing. Humidity is an important parameter, except that in our experiment the box is closed, and so it tends to go to very high humidity. In nature, icicles will sometimes grow in very low humidity, and then the heat transfer by evaporation is significant. In our experiments, it is not significant because we measured the humidity, it's about 80% all the time. The rotation you can try or not, you can turn on the fans or not, you can do all these things. They're actually a large parameter space, okay? And the experiment is very slow. If you're lucky, you get 1 icicle a day. If you really work hard, you can get 2. And so when you think, oh, I grew 180 icicles, that's a lot of work, because you've got to build a machine and keep it working all that time. Okay, so what about the air? Why did we stir the air in the box? Well, at first, I did not intend to stir the air in the box, because as we will see, the idea that the icicle is covered by a boundary layer, a rising thermal boundary layer, is important to the theory. And I thought, let's measure the boundary layer. Let's do still air and see what the boundary layer looks like. Okay? We built the box, we turned it on, we made icicles, and 80% of them split like this. Okay? So for some reason, which I don't understand in detail, as an icicle grows in very still air, and the air inside our box is more still than in most refrigerators, because most refrigerators circulate air. Ours does not circulate air if the fans are on, so it's totally still. They will go what we call legs, okay, or protrusions which drip. So both these tips are growing. And if you turn on the air and gently stir, then only about 10 or 15% of the icicles have legs. And then you have some data, okay? So henceforth, I will almost always use fans on. And we don't, I have to say, we do not really understand why still air causes the legs to grow. It has something to do with the fact that that these angles tend to be 60 degrees. So what I think happens is a big crystal gets growing and it pokes out, and the boundary layer is thick because it's not stirred. And so then it starts to drip, and then you're lost. It drips from both things, okay? So by stirring, we suppress but don't eliminate that. I should also say that multiple tips are often sometimes seen on natural icicles too, so it's not a complete pathology of the experiment. I imagine that this icicle grew under unusually still conditions or something like that. Okay, so here's the most obvious thing to measure is the length as a function of time and the width as a function of time. So this is the radius at 5 centimeters, which is up here somewhere.
Question?
Yep.
When you have legs, do they both grow? Or do you have one that die and the other?
No, they tend to both grow. Sometimes you get a leg that stops, but mostly they grow. You're going to ask me why they grow, but we don't know, okay? All right, so one thing we do know is that you're putting water in at a constant rate, and the icicle is getting bigger and bigger, and therefore the water is being consumed more and more in mode 2, the sides. And eventually the water stops reaching the tip. And all the water, water is still pouring in here, and so this icicle gets thicker and thicker. So it grows for a while linearly, very fast, and then boom, the tip stops growing. And the second thing I will mention is that the temperature and the flow rate affect the rate of tip motion fast, the velocity of the tip, but they have a much smaller effect on the velocity of the radial growth. Okay, we call that phenomenon cessation, stopping. And cessation happens when the flow rate is relatively low and when the water supply is relatively low and when the temperature is low, okay? And I believe that all icicles would eventually stop if they didn't break off, okay? Because more and more water is being consumed, and eventually there isn't enough water to reach the tip, and it will stop. This is another thing that does not happen on stalactites. In stalactites, all the water falls off, so there's never a loss, the water is never used up, okay? So really, the ones that we see stopping are just the ones that happen to stop inside of our 65 centimeter window here. If we had a double-sized window, we'd see them grow longer. Okay, so the velocity of the tip depends on the flow rate and the temperature. This is the temperature of the air. And basically, it's fast if the air is cold. That's not very surprising. And it's also fast if the flow rate, input flow rate, is low. And that's because the drips that are falling off the tip are carrying away latent heat more efficiently for a flow rate. And too much flow rate, and it doesn't grow as fast. But basically, it's not very surprising, but basically there's an inverse relationship. And the flow rate is also inversely related to the flow rate. So fast flow makes slow-growing icicles, slow-growing tips, and slow and small flow rates produce fast-growing tips. These are, by the way, these are all distilled water now. Okay, we're going to get back to impurities in a moment. If you look at the rate of radial growth, it's much less dependent. This is a much more tighter scale here, much less dependent on the temperature and the flow rate. And in particular, it almost doesn't depend on the flow rate, which is maybe a little surprising. This scale is the same for these two, but you see this is quite scattered. There's not a lot of trend there. And this is before cessation, obviously, okay? Interestingly, if you then add impurities to your water, and this is 7 different kinds of impurities, various different impurities, there's still cessation. They still grow and then stop. But right before they stop, they accelerate. The tip accelerates. And if you focus your eye on the tip here, you see it going at constant speed, and then, whoa, it goes faster, okay? So now you're going to ask, why does this happen? We don't have any idea, okay? Nobody knows why this is true. But we see, of course, for large amounts of impurities, the shape is no longer this nice smooth thing. It's much more ripply. I'll come back to that. Okay, so there is a theory about Platonic icicle shapes by Short and Bajents and Goldstein, which is one of the papers that provoked me into this problem. And the theory is very, very simple. In fact, it's astonishingly simple. It says, basically, the icicle is axisymmetric. The assumption is that it's axisymmetric, that it's covered by a thin film of supercooled water. But the temperature drop across the water between the air and the ice is very tiny. It's only about 100 millikelvin, okay? And then the temperature drop from the surface of the water out into the air is like 15 degrees. So you just neglect the temperature of the water, and you neglect all the advection in the water. And then the ice growth is limited by the heat transfer across a boundary layer of air. And the assumption of the model is that that layer of air is laminar. And by making that assumption, you can use this pretty scaling law for laminar boundary layers. You take a uniformly heated plate, from the edge of the bottom of the plate, the boundary layer grows like the 1/4 power of the distance from the tip. So this Z is the distance from the tip. C is a dimensionless number which is related to the Prandtl number, and we just take it to be order 1, okay? And I'll come back to that point. And this length that goes into this boundary layer this is the kinematic viscosity of air, G, the thermal expansion coefficient, and the temperature difference. And that produces a boundary layer of thickness delta. Okay, now you can say, well, how fast does the side of the icicle grow, therefore? And now we invoke something which I thought the previous speaker was going to describe, but now we don't have a previous speaker. So it's something called the Stefan condition. This is the condition that tells you how fast an ice surface will grow. It's basically the rate at which the heat is transferred to the air is equal to the latent heat of ice times the density of ice. That is the amount of heat per unit volume being produced by the surface, times the velocity of the surface. That's the amount of heat that you have to get rid of, okay? Is that okay? Everybody okay with that? That's the most basic thing about ice growth, the Stefan condition, okay? And then we say, okay, the Stefan condition says that all the heat has to cross this boundary layer, and so it's the thermal conductivity of air times the temperature difference across the boundary layer divided by the distance. That's the heat flux, and you just equate that to that, and this is from the model of the thickness of the boundary layer. Okay, and so this gives you an expression for Vg, which is the radial growth. And it should scale like the 1/4 power of the distance, negative 1/4 power of the distance from the tip. And this is a characteristic velocity which contains all those parameters. And then Short et al. Make a brilliant assumption. They say, okay, let's pretend that the icicle is a self-similar shape, a shape which is translating forward but not changing its dimensionless shape, okay? And that puts a condition on the velocity of the sides versus the velocity of the tip. If they're related by this, then they have a uniformly translating shape. So now you write the sine of the angle in terms of the z derivative of the radius of this supposed shape. And then you change two dimensionless variables where you divide both the radius and the distance from the tip by a common length a. And then you write some equations and you get an ODE for this shape. And the incredible thing about it is all the parameters disappear, okay? The speeds, everything's gone, okay? So this is a dimensionless ODE, the best kind, right? There's no parameters left. And it has a very simple, not so simple, but it has a shape which looks like this rather not obvious function, okay? And that they call the Platonic icicle shape. So the provocative claim here is that under all conditions of flow and temperature, all icicles will become the same shape. And that shape, when you scale it, is given by this crazy-looking thing. And it actually reduces to the 3/4 power law of the distance. So the radius goes like the 3/4 power of the distance from the tip for small values of this parameter. And the crazy thing is this parameter looks like this, okay? Now, would you have guessed this? You would not. This is a not obvious length scale. And I would like to point out that it contains as a parameter the velocity of the tip. And all that lovely stuff about the little tube at the tip and the pendant drop and the liquid water in the column, gone, okay? Not even mentioned in this theory. As far as this theory is concerned, the tip is an infinitely sharp point, and nothing happens. There's no physics at the tip. The only thing there is this thing used as a parameter to enforce this, okay?
So this is for pure water?
Sorry?
This is for pure water?
Yes, I'm sorry, I should have mentioned that. They assume pure water here. No impurities were discussed. That's because at the time of writing of this paper, they did not know that impurities were important. Okay, so does it work? That's the only thing you can ask of a theory. Does it work, right? It may be beautiful, but it's also could be wrong. Okay, so what we do is we take 100 icicles grown under various conditions, some with tap water, some with distilled water, and we fit them with one parameter, A. Okay, it's a length. And the good news for the theory is that there are some icicles that fit. Okay, so when we wrote this paper, we had fun with this. Some icicles are platonic, but some are not. Okay, so here are the best 5 of the 100 icicles. And you see it fits very well. And this is even more remarkable because this slope here does not depend on A. It really is dimensionless. So, you know, it could have been anywhere, but it's the right slope. And so you think, wow, it's working. And then you look at the rest of the icicles. Let me get to that in a second. The rest of the icicles, and the worst 5 don't fit at all. Yeah?
In your experiments, what was the typical range for this parameter A?
I'm going to tell you all about it in a second. Okay. So the conclusion of our paper was that, yes, there are some platonic icicles, and some fit the theory to a remarkable degree, even seem to get the slight curvature here. It's not a cone. It's very slightly different than a cone. But the bad news is that most of them, or a very large number of them, don't fit at all. Okay, and why don't they fit? Well, it turns out that the water purity is by far the most important parameter. If you make distilled water icicles, they are much more platonic, although still not perfect. If you make tap water icicles, or even icicles with any impurities in them, then they're, you know, not only ripply, but also the background shape is not very platonic. So here's a carrot, you know, a fat icicle. If you plot the reduced chi-squared, which is the goodness of fit parameter, versus the temperature, there's no trend, except that the red ones are somewhat more platonic than the blue ones, and that's because they're made of distilled water. Yeah?
Looks it's whitish on the right. You want to drop more air bubbles into the icicles with tap water?
You mean this is bigger?
No.
Oh, on the
Picture
figure.
on the right.
Oh,
You have a lot of scattering, it's whitish.
oh yes, I should have mentioned that too. Another difference between the pure icicles and the impure is that here the ice is very transparent, and here you see a kind of fogginess. In the third lecture, I will tell you what that fogginess is. Okay, it turns out to be interesting. Okay, so what happens with the cessation? Well, obviously it can't stay platonic if it stops dripping from the tip. And indeed, that's what happens. This icicle grows for a while, stops growing, and then boom, the value of chi-squared starts to shoot up, okay? And this is a chi-squared of 100, okay? So this is a very bad fit. If you then say, well, we take the parameters we know for the experiment and put them in and calculate a theory, it turns out to be an absurdly tiny number. It's 10 to the minus 7 meters, so it's microns, okay? It's small, preposterously small, I think. And if you take the value that you get from the fit, it's also preposterously small, but bigger, okay? It's 100 times bigger than the theoretical version, but it's still extremely tiny. But there's a single parameter fit. Since A is so small, we would expect to be in the small a limit here. And so we really expect the platonic shape to be this ratio of 4/3 zeta to the 3/4. If you then say, forget the platonic shape, let's just fit to a 2-parameter fit where alpha and beta are the parameters, a power law, a pure power law, you get a fit which is actually slightly better than the 1-parameter fit. That's not a surprise, you have 2 parameters. But the most platonic versions have an exponent beta which clusters close to 1/2 and not to 3/4. Okay? Not looking good for the theory. Okay, so now we can say, well, give me the theoretical value for each icicle, give me the fit value for each icicle, let's plot one against the other. So you plot one against the other, you see the theory gives you this tiny, tiny number, the fit gives you this tiny number, and if this would be a 45-degree straight line if they were perfect, okay? But this one, the fit parameter is around 100 times bigger than the theoretical value. But that comes from taking c equals 1. Remember, there was a dimensionless number in the thing. And since c is raised to the 4th power in here, we can actually remove the discrepancy between a fit and a theory simply by choosing c to be 0.2, okay? I don't know what c should be. It's something of order 1, but 0.2, okay, you know, sort of 1, okay? And so this looks good for the theory, right? If it was scattered all over the place, then you'd think, okay, we're dead, okay? Now we come to Menno's experiment. We used distilled water, but we did not try to use super pure water. And that was a philosophical choice because there are no places on Earth where distilled water flows off of roofs, okay? Even in the center of Antarctica, the water that falls from the sky is not distilled. So the water we use, the distilled water I showed you, is more pure than any natural water. But it is not the most pure you can make. You can make distilled water 10 times more pure by using what's called milli-Q water, which goes through a big process, which Menno can explain. And if you grow icicles from super distilled milli-Q water, and they used a concentration of 5.6 micromolar, and we had about 30 to 50, so about 10 times more pure. And you fit the shapes to cones, and it turns out that a cone is just as good a fit as the as the universal shape. And so that's no reason to use universal shape. You find that when you get to very, very pure water, that it no longer resembles the Platonic shape. It deviates again, okay? And Menno, you call this the dripping candle, okay? And it resembles a dripping candle in the sense that you see little drops running down the outside, and it doesn't look very Platonic, okay? Only when you go to this extremely pure water. So what we call the Platonicness, okay? The Platonicness is not maintained if you make it too pure. So it appears that icicles are Platonic under a sort of narrow range of conditions, okay? The conditions are that if water is pure enough, distilled, then they resemble Platonic icicles. But if you go too pure, they stop resembling. And if you go less pure, they stop resembling. The theory contains nothing about the tip motion except as a parameter. It contains nothing about the ripples. It contains nothing about impurities at all. Okay? All right, so is it a successful theory or not? You know, there's theory and experiment are different, okay? In theory, experiment and theory agree. But in practice, in experiment, they don't agree, okay? So if you're an experimentalist, you would say, oh, this doesn't agree, it doesn't fit the model. If you're a theorist, you say, up in perfect heaven land, in Platonic land, you know, the icicles are Platonic. And there is some evidence for this. Some icicles are indeed Platonic if the water is pure enough, but not too pure, okay? If you allow me to take the dimensionless parameter to equal to 0.2, then I can get A in theory and A fit to agree with each other reasonably well. So those are good things for the theory, okay?
Can you remind us where C is coming from?
It's in the boundary layer equation, okay? So the boundary layer goes like C times this ratio of L over Z to the 1/4.
So it's a fitting parameter a priori, or it could be...
It's purely a theoretical dimensionless number. It depends on the Prandtl number.
Okay.
I don't know exactly how it depends on the Prandtl number, but...
So we could have a theoretical value of that, but...
We do. I just don't happen to know what it is, okay? And I just use it as a parameter, okay? Okay, so that's the good news. If you're a theorist, okay, you can go home and say, we've done it. We've made a theory. The bad news is the theory relies very heavily on that 1/4 scaling of the laminar boundary layer. I use a very simple boundary layer model, okay? And I made icicles in stirred air, and I made them in still air, and I did all kinds of things which screw up the boundary layer, and yet it made no difference. And in fact, the most Platonic icicles I showed you actually occurred for gently turbulent air, and not laminar air at all. So why does the theory work if the air motion isn't like the theory? If I fit to a 2-parameter power law instead of the 1-parameter power law, I get an exponent of 1/2 instead of 3/4. And it's a better fit, actually, because it's 2 parameters. And the thing that bothers me about A is that it's absurdly tiny. If I told you that the shape of an icicle depended on a length scale being physically important, well, but that length scale is 1/10 of a micron. You would go, what? Because, you know, that's just absurd. It's nothing to do with any length scale in the problem. It's much larger, thousands of times larger than the thickness of the boundary layer, the size of the drop, or any kind of physical thing. So A, I don't understand A. Okay, I want to know what A is. Why is it supposedly so small? And then the other thing, that the theory does not do anything with the velocity of the tip. We model the velocity of the sides with the boundary layer model, and then we enforce the shape to be using this self-similar shape equation. In reality, there's a great deal of physics. As I mentioned before, the tip grows faster than the sides because of all these heat transfer and all this stuff. And all of that's gone. There's nothing, none of that's in the model at all. So is the theory a success? So I say, well, it's a qualified success. You decide, okay? It's a matter of taste, okay? If you're the kind of person who likes to nitpick, then you're in this camp down here. If you're the kind of person who imagines that the simplest, most beautiful shape of theory is the right one, then you're in this camp, okay? You can decide. Okay, how much time do I have left?
15 minutes will be good.
Oh, I can stop before that.
10 minutes.
Let me just make a pause then. So one of the things I like to do is I like to write Python code to animate data, okay, just because I like to look at it. And so here is a whole bunch of icicles moving, all distilled water icicles, and this is the end of the formal part of the talk. Now I'd like to describe what I did with this data in the outreach way, okay? In Canada, if you get a grant, starting I think last year or something, you have to make all your data public because the government is paying for your experiment, so you must make the data public. And years before that became in, I fell in with some librarians, okay? And librarians are very worried that books are disappearing, okay? So they want to be data librarians. And they know about this coming requirement. So I got talking to them and they said, why don't you archive all your data in this Dataverse thing, which is called Hyperborea, I think it's called. And it's the Canadian National Database for Data, okay? So I assembled all the data together into something I call, all of Anthony Chen's data together, into something I call the Icicle Atlas, and I released it to the world under Creative Commons 4.0. So that means if you want to make a Christmas card which shows an icicle, you can download an icicle from my data, and you don't have to pay me, the government has already bought it, and all you have to do is say, I got this from the Icicle Atlas. And every run of the experiment has a little home page, and the network is not working, so that you can't follow this link. But if you Google Icicle Atlas, you will find it. There are about 230,000 raw images in the database. Hundreds of movies of the kind I've been showing you. And it's all free to the world, okay? And I call it the Icicle Atlas. And there's two versions. The version is just HTML. So I wrote Python code to produce HTML to take the data and just pour it out onto a web page, okay? And then at the same time, we poured the data into the Dataverse where it's downloadable and citable. So that means if you want to write a physics theory about it and you need a picture of an icicle, you can say, this icicle in figure 1 is number blah, blah, blah from the Icicle Atlas site, okay? It has a unique URL that you can point to it, okay? So this is archived data. And it's also free to the public, so it's outreach in that way. And all the movies are archived there, all the images, all the associated zip files of all the temperatures and everything like that. And I made something called the Icicle Rogues Gallery. A rogues gallery is when you take pictures of criminals and you line them all up and you ask the person, which one of those guys beat you over the head? Oh, him, okay, that's the rogues gallery. So here, this is a small sample of the icicles in the rogues gallery. So you think, I kind of like that one. You click on that and you know everything about that icicle, all three-dimensional shape, including, in many cases, downloadable STL files, that is 3D files. So if you're interested in 3D printing, you can go to this database, download a 3D picture, a real icicle, you know everything about it, and you can print it on your home printer. Okay? And then there's a thing called Thingiverse. Has anyone heard of it? Thingiverse is the proprietary 3D file database for this 3D printer called a ThingMaker. And there are icicles on there now, and people all around the world have made icicles out of that. Now, as a result of this, I received a great deal of press. The press loves a funny story about science, especially if the scientist is odd, okay? And if you look at science stories, there's two kinds of science stories. One is where the phenomena is profound, like the Big Bang or whatever. And the other one is where the scientist seems like a strange character, and it's an interesting story. So Stephen Hawking is the only person who hits both of those categories, okay? But I released it to the world. We made a press release, and it was picked up by the New York Times in March 16, 2015. The Icicle Atlas was covered by this wonderful writer named James Gorman. And he and I had a phone conversation, and he published this beautiful account of the Icicle Atlas. And for about a year, I was doing press releases and talking to various people and giving talks to the public. And so we got a lot of hay out of the Icicle Atlas. And the reason I called it, by the way, the Icicle Atlas is that there's an interesting book, which I urge you to read, called The Cloud Atlas. And so the idea of an atlas of icicles, I thought that was kind of interesting. Okay, that's the end of my talk. I'd be happy to answer any questions, yes.